So this next piece will be on work, average value, and then a bit on 4A. So work. So in terms of physics, there's a definition to what work is. And so work is a force applied over a distance. It is what work is in physics. And so here in terms of calculus, we get that work then is given by the integral of a to b, f of x dx. Right? So in terms of example, how does it work this out? And that would be find the work done. By a force F moving an object from x equals 1 to x equals 2 according to the f equals f of x, which is given by x squared. Okay? So really all we want to do is we have our function, which is x squared, and we want to integrate it from 1 to 2. So we get that the work is going to be interval 1 to 2 of x squared dx. If we integrate x squared, we end up with x cubed over 3. So x cubed over 3 evaluated from 1 to 2. So this comes out to be 2 cubed over 3 minus 1 cubed over 3. So 2 cubed is going to be 8. So this is going to be 8/3 minus 1/3, and we end up with 7/3 for our answer. Okay? Another example of this deals with work done by a spring. So work done by a spring. And so for this, we're going to have to make use of Hooke's law. Which says that f of x is given by k times f. And k is the spring constant. Okay? And basically what k is a measure of is basically how stiff is the spring. So the higher the k value, the harder it is to stretch that spring out. So if you think the difference between a spring you may have on a pen compared to the spring you have on a garage door. So an example in terms of how this would work for this type of way. Let's say we have a spring, and it requires 12 pounds of force to stretch 10 inches. And we want to know how much work is done to stretch it 3 inches. So with the first bit of information, we can actually get the value of k. And so we got f equals kx. And so we got 12 equals k times 10. So so k is going to equal 12 over 10, which will be 6/5. So that is the k value for our spring. And so f of x for my spring will be given by 6/5 x. And so this is what we're going to use in order to get the work done. And so the work done is going to equal the integral 0 to 3, 6/5 x. And so that would be the same thing as saying we're going to integrate 6/5 0 to 3 of x. And we do have our dx out here. So this will be 6/5 of x squared over 2, evaluated from 0 to 3. And so we get 6/5. This is going to be 3 squared over 2 minus 0 squared over 2. So this will be 6/5. This is going to be 9 halves. The back part is going to be 0. And so we can simplify that part out. And we end up with this. Will give us a final answer of 27/5 inches. Right? So we get our work done by our spring in this case. Right? The next thing then deals with average value of a function. So that is given by the y average value is 1 over b minus a integral a to b f of x dx. This is my equation for finding the average value. So in terms of example one of this, so let's say I want to find the average value. So find the average value given that f of x is equal to x squared, and I want to know the average value from 1 to 4, right? So a is 1. B is 4, right? So we're going to integrate. It's going to be 1 over 4 minus 1 integral 1 to 4 of x squared dx. So 4 minus 1 will be 3, so this will be 1/3. This will be x cubed over 3, evaluated from 1 to 4. And so the next part then is to plug in our numbers and get our value here. So this is going to be 1/3. This will be 4 cubed over 3 minus 1 cubed over 3. So it'll be 1/3. 4 cubed is going to be 64. And so we end up with 1/3 times 63 thirds. Okay. And we end up here with the final answer, which will come out to be 7. So the average value of the function over that interval will be 7. Right? The last part then deals with something that comes from sound, and that deals with Fourier and Fourier series. Right? So we had in sound, physics sound, how about Fourier, and that any complex wave can be written as a sum of sideways. See? So you got in terms of a Fourier expansion. So you got f of x divided by a naught a1 cosine x a2 cosine 2x plus a sub n cosine nx plus b1, right? Once again, b1 sine x b2 sine 2x plus b sub n sine nx, where n is the integers 1, 2, 3. And then you got these coefficients a naught, a sub n, and b sub n. And those are determined by a very calculus. So a naught is given by 1 over 2 pi, integral 0 to 2 pi, f of x dx. That gives us the value of a naught. A sub n is given by 1 over pi, integral 0 to 2 pi, f of x dx, and f of x, sorry, f of x cosine, cosine nx dx, and again, n are my counting numbers. And then lastly, b sub n is 1 over pi, 0 to 2 pi, f of x sine nx, nx dx, right? And again, n are the integers 1, 2, 3, so on. Right? So let's go through one example as to how this would work. Okay. Again, just for going through it, there won't be any test questions. This won't be on the final. But just in terms of how this works. So we did talk about it in some. Okay. So we want to find the Fourier series. For the following. Okay. We got f of x is equal to x, and from 0 up. Okay. All right. I like it. All right. Not sure how that ended up, right? Try this one. F of x is equal to x, 0 less than or equal to x less than or equal to 2 pi. Okay. So we need to find our coefficients a naught, a sub n, and b sub n. So for finding a naught, we have this. So finding a naught is going to be 1 over 2 pi, integral 0 to 2 pi, x dx. Right? Well, if we integrate that, it's going to be x will give us x squared over 2. So this will be 1 over 2 pi, x squared over 2, evaluated from 0 to 2 pi. So the next part is to plug this in and see what we get. So this will be 1 over 2 pi, And this will give us 2 pi squared over 2 minus 0 squared over 2. Well, the back term, 0 squared over 2, that'll go away. So we end up with 1 over 2 pi times 2 pi squared over 2. So my 1, 2 pi here will cancel out the exponent there. And we end up with 2 pi over 2, which will give us that this will be pi. So we have A naught is going to be equal to pi. Okay. So that's our value of A naught. Okay. So now we go on to finding our values of E. So we're going to do, okay. So our formula for finding A sub n was given by 1 over pi integral 0 to 2 pi f of x cosine nx dx. So in our example here, we got 1 over pi integral 0 to 2 pi f of x is x, so cosine nx dx. And again, and our incoming numbers. Right? So we want to integrate this part, and so this form here matches up with a table, and now we handed that out. But in the books, in the calculus books, you'll find usually in the back, and I gave one out in abbreviated form last week, which I think had 20 different forms for intervals. But you can find expanded tables of intervals, somewhere, depending on the book, up to 100 different forms that are used. And so this comes from one of those forms that are in those kinds of tables. Okay? And so if we integrate this, we end up with one over n squared cosine nx plus nx sine nx. And then, of course, we would then evaluate this from, that would be plus c, right, for that part of it. Right? But then we actually are, this is going to be a definite interval. And so if I do this with my definite interval, we got that A naught will be 1 over pi times n squared cosine nx sine nx evaluated from 0 to 2 pi. So now it's a matter of plugging in the numbers here and seeing what this comes out to give you. And so if we do this, we got this will be 1 over pi n squared. This will be cosine of 2n pi plus 2n pi sine 2n pi. For that part, that's what happens when I plug in the pi. minus the cosine of 0 plus n times 0 sine of 0. Right? And so this will be the back piece. Right? All right. So this is going to be 1 over pi n squared. Right. So the cosine of 2 pi is 1. And so the cosine of 4 pi is 1. Cosine of 6 pi is 1. So this is always going to be 1. Right? The sine of 2 pi is 0. Right? Sine of 4 pi is 0. So this term will always be 0. Right? The cosine of 0 is 1. And the sine of 0 is 0. And so you end up with this. Well, this all goes away because 1 minus 1 is 0. And so we get that this is going to have a final value of 0. And so our value for a sub n is going to be 0. Okay. So now we go to our b sub n, the last coefficient. So b sub n was given by 1 over pi interval 0 to pi. Let's go back to the original formula. 1 over pi, 0 to 2 pi, f of x sine nx. So again, in terms of our example, we got 1 over pi, interval 0 to 2 pi, x sine nx dx. You get that? Again, this form is a form you can find in terms of in tables. So don't have to worry about trying to figure it all out. There's tables that have these kinds of things. And so if I integrate this by using the table, we find out that this part will be 1 over n squared, and then it'll be sine nx minus nx cosine nx for that part of it. And this we can combine a little bit, and so we end up with 1 over n squared pi sine nx minus nx cosine nx from 0 to 2 pi. And again, we can evaluate this. Right? So this is going to be 1 over n squared pi. And then this will be times the sine of 2n pi minus 2 pi n cosine 2 pi, okay, 2 pi n rather. Minus 2 cosine 2n pi. Okay. So that's what happens when we plug in our pi, and then it'll be minus what happens when we plug in 0. So sine of n times 0 minus n times 0 cosine, barely get this in here, n times 0, right? And not quite gonna fit. So if I simplify this, and what we end up with here in terms of this, well again, sine of 2 pi is 0, any multiple of 2 pi will also be 0, so this part will be 0. In terms of my cosine, this is going to be 2n pi. And in terms of the back terms, this will be a 0 and another 0. So we end up with, in terms of this, we're going to have 1 over n squared pi times a minus 2n. So this will give us a minus 2n pi over n squared pi. And if we simplify this, the pi's will go away. This end cancels that end out. And we end up with a minus 2 over n. Okay. And so our value for b sub n is given by that. So now we can write out our expansion for all this. Because after all, b sub n is given by this, then we would have that b sub 1 is going to be negative 2 over 1. B sub 2 is negative 2 over 2. B sub 3 would be negative 2 over 3. So on, so on, and so on. Right? So we end up that our Fourier series for this particular problem will be given by f of x is our first term we found, which was a naught. We said that was pi. The b term, a sub n terms all went away. And then we get our other terms, minus 2 sine x minus sine of 2x minus 2/3 sine 3x minus, and then this would go on and on, depending how many terms you want to go. So there goes our Fourier series expansion for this particular problem. Now in terms of what that will look like, and what this comes out to be is, so this table are the table of values for that expansion. This is when I only have the first few terms, so basically as I work across, I'm adding more and more terms to it. And so I get that table of data. And then if I do the graph of what happened here, and I also have that here, so we give my graph of this particular function as I add more and more terms, okay? And so the red, this one, is just pi minus 2 sine x is given by that one, right? In this case, the green graph, this graph, is pi minus 2 sine x minus sine 2x is that one. And then lastly, the purple, okay, is what happens when I do the first number of terms. So this is pi minus 2 sine x minus sine 2x minus 2/3 sine 3x, and that would be, right? So the more terms I add, we can see that if I look at this, we see that this is becoming a sawtooth equation, right? So it goes down, goes up, goes down, goes up, all right? And so the more terms I get, the closer I will get to that shape, okay? And so if we do the same thing with, giving the square wave shape. The more terms I add, the better my curve approximates that thing, right? Check out in terms of 4A and 4A series and how those can be used to generate the various waveforms, right? And that will conclude